talking and we'll see. Okay. Nice PowerPoint.
Right. Okay.
So yeah, that's your view up there. Have a seat.
Yeah.
Show was good?
Yeah, except I always get sleepy.
Yeah, we don't have enough sleep.
It was excellent. Fun talk, and then the clarity of it is always so good now.
Yeah. There's a few people in the planetarium show. Was it pretty full in there?
Yeah.
That's too bad.
How's this? Okay, good.
Did you say that? You already remember why I don't have going in there.
I do that.
Please take a seat. We'll get started. Okay, everybody, welcome to our September meeting of the Santa Barbara Astronomical Unit. First Friday, Thursday the 3rd? No, 5th? 5th, yeah. Anyway, as you all know, because you all got here on time, we're changing the time. We're going to give the museum a little more time to get the parking lot clear in the evening and not keep the staff here very late. So we're going to move up a half hour. So this meeting will start officially at 7 o'clock. We're already 15 minutes late because we had such an interesting video in the planetarium called The Edge of Darkness. So we're going to abbreviate some of the stuff we go through at the beginning of the meeting and get right into our speaker. First of all, what we usually cover is the merge manager. Do you have anything you want to, our advertisement?
Well,
Okay, we'll keep it brief.
yes. Thank you, Jerry. My name is Pat McPartman, and I'm the merch manager. And the merchandise is on sale from 6 to 6:30. So I had calendars, I had mugs and caps and all sorts of goodies. So if you want a calendar, you'll have to see me next month from 6 to 6:30. I believe that's the 3rd of October. But if you have any requests to make, my email is merchmgr@sbau.org. So back to you, Jerry.
Okay, thanks. And all this stuff is on our website at sbau.org, not .com, but .org. And we'll go to, Chuck, do you want to go over your outreach for the month?
Sure, just quickly. It's a quiet kind of month.
Okay.
Somebody, was this in the planetarium?
Yes, that's mine.
Oh, right here, okay.
Thank you.
Okay, we already had Telescope Tuesday, so tomorrow night is Refugio State Beach. I don't know if Pat and I are going to be able to make it, so if you like dark skies, please come out with a scope. And then on Wednesday the 10th, we'll bring telescopes down to Carpinteria State Beach. And then on the 12th, on Friday, we're helping out a winery in Los Olivos that's having a party, and the details are on the webpage. It's 2625 Santa Barbara Avenue. And then on the 13th, second Saturday of every month, it's public store party here. It's going to be from 8 to 10. We're moving a little bit earlier because the sun is setting a little bit earlier. And then third Friday of every month is Westmont College. So that's it. It's a quiet month. But schools are going to be ramping up, so we'll have more of that come in November. Thank you.
Thank you, Chuck. Now, anything else that we have up here in the form of business, club business, that can be handled at the second Saturday administrative meeting. So we'll introduce the vice president of the club, so he can introduce Ish. Yeah, and on the, they've got my picture, but it'll soon be his, under Ish. So if you're looking at this out there, I'm not Ish. I'm Jerry Wilson. Okay. Okay, sir, thank you, Mr. President. Lovely wife, Pat. I got a few things I want to do, but we have till what, 9? Which is almost too
We have to
long.
be out by 9.
Out of here by 9,
So
okay.
that includes questions and answers, so.
We had Q&A following Ish. Ish, you got a crowd. Where are you, Ish? Okay, I got a couple things I want to do real quick. I want to do what I call my entrance poll. In elections, they have what's called exit polls. But it occurred to me within the last couple of years at these meetings that they're not all meetings of just our people, our members. We get more than half the crowd as newcomers, potential new SBAU people. So if you're a newcomer, first time ever, I'd like to have you raise your hand and let us welcome you. First time ever, oh, okay. For the benefit of the members we'll be talking to in a second, put your hands back up so we'll know who to buy the beer for later, okay? If you've been here before but you're not a member of SBAU, raise your hand right now. All right, we did something right. Thank you for coming again. Maybe it's $20, you know, for a year. That's about what you get at a meal with a drink in a typical restaurant these days. Members, proudly, SBAU. I want a high five. Okay, we got a good crowd, and I'm going to tell you a couple of things before I invite up our distinguished guest. Tonight, Galactic Atmospheres and Rainfall. I don't know where Ish is from, but I'm sure he'll tell you. And I just wanted to plug a couple things about our fun club, the Santa Barbara Astronomical Unit. It used to be the SBAC back when Alex Filipenko was a member as a kid. He's coming next month. I'll tell you about that in a minute. Astro Hour, that's the name of our vlog, which is well into its 5th year on Monday mornings. If you know the 4 letters of our acronym, just add Astro Hour, SBAUastrohour.com. No, that's it. That's not a website, that's a YouTube video. Please find my seat if you'd like next to me. That's the guy I was sitting before, sitting over there. That's right next to that jacket.
Right here.
Right next to the, okay, sit with the ugly guy behind us.
It takes one to know one.
If you're getting along in the years, you've retired, let's say you were a secretary or worked in money, this club can use you, starting in the new year. Because we're going to lose Tessa, and I think Mrs. McPartland would love to lose the, yeah, she's giving a thumbs down, no? You want to keep being treasurer? Okay, forget the treasurer part. Just run away with the money anyway. So anyway, I just wanted to pay tribute to the people who are part of our Astro Hour vlog, 11 o'clock, SBAU Astro Hour on YouTube, into our 5th year. The ones in the room over here are our president, Jerry, and Outreach, Chuck McPartland, is on the big screen. We have webmaster, Bruce Murdoch, I saw you, there you are, he's on the screen, all these ugly mugs you'll be seeing. Tom Todd used to be with us. Tom Whittemore is our newsletter editor, former Westmont science teacher, and Tim Crawford may be watching us online. So, look at this. Tom, I gotta tell you, I had no idea how irreplaceable you are, man. If something happens to you, what do
We
we
can all
do?
be replaced.
Because we lost Chrissy, didn't we? Chrissy Cook used to do it. She went back to the classroom.
Okay, I just want to talk about the future. Let me skip next month and go to November 7th. Friday, we'll be back in here for Dr. Phil Korngut, Caltech, speaking on a great new NASA project that he's involved with called SphereX. I want to thank Tessa, our outgoing secretary, for getting me him, because he spoke to the Mount Wilson Foundation May 10th meeting earlier this year, and they charge $50 to get in, and they get a full house. And the first thing I told her when she recommended booking Dr. Korngut is, we can't afford a guy that goes to a talk of $50. She said, call him anyway. I did, and he jumped at it. Said, I was just up there at your museum with my daughter. I'd love to come back and talk to you guys. And he picked November 7th. Now, here's the big part. Friday, December 5th is our yearly in-house members-only presentations. Tessa probably won't be able to do her talk on dark energy, though we were looking forward to it. She had health problems, and she's also stepping down out of the secretary, and we could use a second speaker. Is David Grossman here by any chance? Okay, David is an incredible member who is so low-key nobody knows. He's written 5 articles for Astronomy Magazine, and he's a good friend of mine. He used to run the symphony in town, and before that, he ran the music department down at Paramount Studios in Hollywood. And he comes to many of our events. And of course, my favorite local professor of astronomy from City College, raise your hand, Dr. Sean Kelly. What we do in December, instead of hiring speakers, we have at least 2, sometimes 3 for an hour in this room speak from our club membership. Yeah, I call it the in-house, members only. And because Tessa's not available, we're suddenly open for another person, because David Grossman is going to be talking about one of his articles that he wrote. It was a cover story on Astronomy Magazine called Sonification. Something about sounds in space. I have no idea, but he's finally going to do it. I've been working on it for years. I just need a second one. If we don't get anybody, then we'll have an incredible, riveting report from either the president or our outreach coordinator. Next month, in the big auditorium, Fleischman, Alex Filipenko, UC Berkeley professor of astrophysics, world-renowned, had his start right here at DP High School in Goleta in the 70s. And he was in our club, which back then was called the SBAU, Astronomy Club. And he's going to be talking, let's see, did I write down his, no I didn't, but it's black holes, supernovae, and a weird universe or something like that. Subheaded, my inspirational years growing up in Santa Barbara's astronomy club. And he's well known. For some of us, he's right up there with Neil deGrasse Tyson and Brian Cox. He will be here, and it's probably going to be crazy, a big full house. So plan to come. It's free, and we'll also be meeting a half hour early, just like tonight. So ladies and gentlemen, without further ado, Ish Kaul, grad student, UCSB, Galactic Atmospheres and Rainfall. You can start your way up here, if you will, working a range of topics in computational astrophysics, including galaxy formations, black hole accretion disks, more recently solar physics. Ish received his undergrad degree from Princeton, where he worked on galaxy simulations and plasma physics. When this young man was not solving mysteries under interstellar gases, he can be found experimenting with the physiology of percussion. You didn't bring your drum set.
I did not know.
Keep up your chin.
But you play drums.
Yes.
You're going to tell us where you're from.
Yes.
And you're going to remember us like Philip Pino in a few years. If you become famous, you're going to come back. Right? Ish Kaul, ladies and gentlemen.
guess I can start. Hi everyone, I'm Ish Kaul. I'm a fourth-year graduate at UCSB. I'm originally from India. I've hopped around a couple places, but mainly I would say from New Delhi, which is the capital. What else would you want me to talk about? Yeah, yeah, of course, yes, I will remember. If I ever get as famous as Alex, who is pretty actually very famous in the field.
Which department are you in at UCSB?
I'm in the physics department. Yeah, I mean, we have our astronomy and physics department is the same, unlike some other places which are like separate ones, but here it's all combined. In my undergraduate days, I was actually a physics major, even though we had an astronomy program. And then until, I guess, in my senior year, I realized, oh, I've been making a mistake. I should have been doing astronomy. So I was like, oh, there's no other field that is so rich with physics that basically every single field of physics has sort of touched astronomy in some way or the other, and that sort of draws me to astronomy in general. So I hope to share a little bit about what will be a part of my thesis eventually. And the title of my talk is Galactic Atmospheres Rain, which seems like a weird title, but the basic idea is that I'll be talking to you about galaxy formation and evolution, which is how galaxies evolve and how galaxies form, and what our research group has our effort in. And the way we'll sort of go about this is by looking at one important research question that has emerged in about the past 2 decades.
That's good.
And while we're trying to explore,
That's good, Chuck.
while we're trying to explore how astronomers figure this out, we also learn about the tools that astronomers use these days. Astronomers and astrophysicists. There's a very tiny difference, though. I'll tell you about that in a bit. So I'll tell you about the tools that astronomers have to use at the moment and the ways in which we're able to solve this question. And along the way, we sort of unravel the secrets of how the universe works and how galaxies work. So this talk will sort of be applicable to most galaxies that we see. In some cases, we don't have observations that are able to do it, but with upcoming telescopes and with recent telescopes, we're actually able to probe a lot of the physics that you will be seeing in this talk. And as much as I am a theorist, astronomy at the end of the day is an observation-driven science. So I will talk about things that are very theoretical, but eventually everything has to be verified from observations, if not actually stemmed from these observations. So just to start off, to get everyone on the same page, here's 2 pictures of galaxies. I mean, when you think about a galaxy, this is probably what you would visualize, right? So just to engage with you guys a little bit, one of these pictures is real and one of these is fake. How many of you think that? So let's do it this way. How many of you think the left galaxy is fake? Raise your hands. Okay, and how many of you think the right galaxy is fake? Raise your hands. Okay, so those who said the left galaxy is fake, give yourselves a pat on the shoulder. Because the left galaxy is actually from ChatGPT. I actually just entered this one prompt which was that create a realistic image of a galaxy, as real as you can make it, and it spit out that one. It's actually a pretty good impression of what a real galaxy does look like. The galaxy on the right side is actually from a very famous telescope called the James Webb Telescope, which was launched a few years ago. I still remember when they got their first data set, I was sitting in my undergraduate auditorium, and we were having a watch party. So everyone was like, oh, we have to wait for the James Webb Telescope results that are just going to come out, because it was the new and exciting thing in astrophysics at the time, and still is, actually. So the James Webb Telescope was sort of very important in terms of exploring basically almost every field of astrophysics, from what you heard about last month, for those of you who were here, exoplanets, for galaxy formation, for and a lot of other exotic phenomena as well. So it's been instrumental in sort of a lot of fields of astronomy, and as you can see, you can get very, very detailed pictures of galaxies which are real, and often look like, well, there's no way we did that picture, but actually we did, which is really cool. And you can do that with the James Webb Telescope, which is fun. Before the James Webb Telescope, the best telescope that we had was the Hubble Space Telescope, which I'm sure a lot of you would have known. So there's lots of fun pictures online. You can just do one Google search to show that, oh, here's the Hubble Space picture, Hubble Space Telescope picture, and here's the James Webb Telescope picture. And you can do a side-by-side comparison and see what 15, 20 years of difference in technology has made. So that's pretty cool. But here's what our research question is going to be. So assume that, say we look at the Milky Way galaxy, we're just looking at the galaxy from a bird's eye perspective. And you take all of the gas in the galaxy, well, you know how much it weighs. And then you exclude dark matter and stars and things like that. You're only interested in the gas. And then what you do is you say, okay, if all of this gas was used as fuel to form stars, because as we know, all of this gas is used to create stars eventually. Because just a basic overview of how star formation works is you have sort of these clouds of hydrogen gas, and eventually, if they become too heavy, they sort of collapse under their own gravity, forming these molecular clouds. And eventually, these collapse and form stars, and because of their own gravitational force. So eventually, what happens is, in some pockets of the disk, you'll have stars formed, and it turns out that in the Milky Way, you can see that the star formation rate, that's what astronomers call it, is about 2 suns per year. And what I mean by that is that in every 1 year, the Milky Way galaxy produces about 2 solar masses, which means 2 suns, 2 of our suns every year. So if you take this calculation and try to estimate, okay, at what point will we run out of all this fuel, right? And run out of all this gas to form stars. And you will reach a very weird conclusion, which is that it will only take 2 to 3 billion years. For those of you who know astronomy, you know why this number is weird. The reason this number is weird is because, well, one, the Earth itself is about 4.5 billion years old. And the Milky Way universe, and the Milky Way galaxy, as we know, is about 13.5 billion years old. So how is that possible? So this is one of the main questions that we'll try to answer today. And the way we'll do it is, well, we sort of already had hints to this answer. We sort of knew what we could do to make this question not a question. And the way this happened was by looking at galaxies not like this, not through the bird's eye view, but looking at it the other way. So the main question is, what is going to save our galaxy from its ultimate death? And the answer is that galaxies don't all look like this. So if you look at a galaxy edge on, not all galaxies, but a lot of galaxies, if you look at them edge on, you'll see a lot of this extra gas floating around. Both of these are real pictures. They're taken from real research papers, and they show you actual galaxies that people have imaged. And you'll see there's all this extra gas that's floating around. So that means we do have some gas at our disposal. So there's some reservoir of gas that we haven't accounted for when we take the disk calculation. Now, the only problem with this story is that the gas that is around the disk of galaxies is not that much. It's only, in the Milky Way case, it only occupies about 2% of the mass. So that's almost nothing. But then what astronomers have now emerged with this picture, which is this whole idea about galactic atmospheres, similar to atmospheres, hence the title of my talk, similar to the atmosphere of the Earth, which is that you have this whole medium, which is called the circumgalactic medium, that engulfs the entire galaxy. And this is sort of like a big spherical halo, and the disk sits inside that halo. And so the idea is that there's various processes that happen inside the disk, which sort of eject gas into the circumgalactic medium, and vice versa, this gas is also able to come back down onto the disk. And so you have sort of this, much like the water cycle on Earth, where you can have water evaporating and then coming back down as precipitation or rain, you can have a similar process happen in galaxies as well. Hence the title Galactic Rain and Atmospheres. Now, we'll get to what that means in practice, because of course we're not actually talking about water, we're always talking about gas. But what does this mean in practice? So, well, you could ask, why do we even want to model this in the first place? Why do we want to use theory? We can just use observations and figure out this answer for yourself. And the problem with that is that galaxies evolve on very, very slow time scales, over about millions of years. So if you ever hope to see what happens as a galaxy evolves, that's going to be impossible. So because when you actually take a picture of a galaxy, you only take it as like a snapshot. You don't actually see how it evolves. And this is why we need theory. This is why we need to understand how galaxy formation happens. And this is why we need to understand where galaxies get their extra gas from, where they get all this extra mass from, and how do they evolve, how do they form. Questions such as this. So how do we actually go about modeling it? The answer is actually surprisingly simple. You do it like soup. Now, I tell you what this means. It's a weird analogy, but you'll see in a second why this works. So, imagine, you know that all of the galaxies basically only composed of gas. Well, primarily composed of gas. There's many other things that the galaxy is composed of, but it's primarily gas. And which gas, you may ask? It's all hydrogen gas. So it's some combination of atomic hydrogen and ionized hydrogen. What do I mean by ionized hydrogen? Well, think back to high school chemistry, right? So hydrogen is basically just one electron and one proton bound together. So you can imagine that at some point the temperatures get high enough and the pressure gets low enough that you can actually knock out the electron from its outer shell and you can get it to be ionized. Which means it's possible that you basically have this soup of ions which are positively charged and negatively charged electrons sort of moving around together. That's what most of the galaxies is composed of. And in physics terms, that's called plasma. That's the whole idea. So the basic definition of plasma, which some of you may know as the fourth state of matter, is just this. It's this soup of positively charged ions and negatively charged electrons. That's the basic idea. So if you want to go about modeling this plasma, how do you actually do it? It turns out the answer to this is very simple. And the reason it's very simple is because the galaxy is just so big that you can actually think about this galaxy as a fluid, which is weird. I just told you it's a gas, so why would you say it's a fluid in the first place? But the basic idea is that you can actually think of anything as a fluid as long as you think about length scales. So because the galaxy is so huge, you can imagine what defines a fluid and what defines a gas. If you think about a gas, you just think about, oh, you have random particles just moving around everywhere in this room, for example, like air, right? And eventually you might have maybe one random collision or two random collisions, but by and large, most particles are just free to move around. But think about what happens in a galaxy, right? It's the same idea. You can have one collision randomly or two collisions randomly. Most of the time, the gas is free to move around. But the entire system is so big that you can just assume that all these collisions are frequent enough that I can just think about it as a liquid. And it turns out to be an excellent assumption. You can use this. And so in the 1700s, we had this very famous Swiss mathematician, Leonhard Euler, who developed these fluid equations, which means it's sort of able to, the equations are able to model any liquid flow on Earth. That was the main purpose of the model. The main purpose was that, oh, you have liquid flowing through a pipe. How does the pressure change? How does the density change? Things like that. But you can actually use it for galaxies as well, which I think is one of the cool things in astronomy, which is that the same equations used to model soup. Yes?
So what you're saying, I think, is that the driving force of the gas is density gradients. It's not,
That's part of it,
not
yes.
electric fields and not magnetic fields.
We get to that
Okay.
soon. Yes. Yes. That's gonna come in later. Yes. I'll get to that in a second. But I like where your thinking is headed. Yes.
The president, he gets these things early.
Yes. So that's the idea. You can think of all of this as a liquid, and if you think of this as a liquid, the equations simplify immensely. But this is not all there is to it. This is certainly part of the story. The other important piece of physics is that, say you had a very hot bowl of soup, you just prepared it, and you left it outside on the table. What's going to happen eventually? It's going to cool down. And that's the other key part of physics, which is called radiative cooling in astronomy speak. So this is very important. So you have this plasma, which is quite hot, but there's physical processes that act to cool it down, right? And that's what we call as radiative cooling. The third important piece of physics is supernova explosions, which you just heard about, actually, in the talk, where you were told about type 1a supernova explosions, right? So in the life cycle of a star, if the star ever exceeds 1.4 solar masses, which is famously known as the Chandrasekhar limit, you can actually get a massive explosion that stretches light years across. The first such explosion that we saw was actually in the year 1054, and that was this explosion of the Crab Nebula. So this is what it looks like now, but in 1054 is when it was at the peak of its activity. It was sort of still in the exploding stages. so to say. And this is actually what motivated the famous astronomer Charles Messier to start his whole M catalog, which a lot of the astronomers would know because he has about 100 objects or so. And this is actually frequently used as like a rough blueprint for astronomy enthusiasts to look into the sky and try to identify all these objects. So Charles Messier was actually trying to look at comets, but then he saw the Crab Nebula explosion, and he was like, oh wait, it's not moving in the sky, so it must not be a comet. So he called it a non-comet object, and this was the first non-comet object that he had. And that's why it's the M1. It's the first on the Messier catalog. So that's the Crab Nebula for you. Lots of history attached to it, lots of philosophy attached to it, because Chinese astronomers, Islamic astronomers, Persian astronomers observed it, and they were so puzzled. They were like, oh, what is this? And they developed a lot of philosophical theories based on this, which was interesting. So for our purposes, all we care about is how to model a supernova explosion. There's actually huge industries of people that are trying to model how this works. So the star in the center, or the supernova itself, that's a whole field of study in astronomy. So people spend their entire careers trying to model how the explosion happens and how the explosion sort of influences the environment. The other aspect of this is you can see all these really cool structures that happen around it. And this whole thing is called a supernova remnant, which is basically so there's lots of models that are developed trying to understand what is the impact of this explosion on the surrounding gas. And most people now seem to agree that since you have all these tiny thermal bombs that are being set off all around in the Milky Way galaxy, this sort of acts to drive turbulence in the galaxy. And what do I mean by turbulence? I just mean it makes it sort of frothy, which is not unlike what happens when you're boiling soup. Hence the analogy. So you're trying to model soup, and these are sort of the key pieces of physics that you need to include. And once you sort of have these, you can try to model what the galaxy itself evolves like. Now there's only a tiny problem. If you think this is all that there is, it's not. We've missed out all of these extra things, right? So we haven't included any of this physics at the moment yet. And all of these are actually very important, if not more important than the things I discussed, actually. So my personal favorite is magnetic fields, as you had alluded to. And the reason magnetic fields are important and electric fields are not is very interesting. So when I said you have a plasma, you have positive and negative charged ion, positive charges and negative charges. Eventually what happens is, because you have movement of charges, you're going to develop electric fields, of course, high school physics. But because you have moving electric fields, you also develop magnetic fields, also high school physics. But eventually what happens is, because you can cancel out magnetic fields, like positive and negative charges cancel, over large scales and over large times, we can assume that everything is charge neutral, which means there's enough positive and enough negative ions, enough negative electrons to sort of balance themselves out. But this does not happen with magnetic fields. You can't get rid of magnetic fields. There's no such way to do it. Because there's no positive magnetic field, there's no negative magnetic field. And that's why you usually don't need to worry about electric fields at all, but you do need to worry about magnetic fields. And they have very interesting applications when you try to model it, which we will get to in about 10 minutes. The other important thing that I did not talk about is black holes, which I think you guys had a couple talks by speakers before on black holes. And the reason black holes are important is because black holes sort of sit at the centers of these galaxies, and so they're very important in their evolution, obviously, because they are the ones that are sort of driving the whole accretion of mass into a disk. And they're the reasons why you have something that looks like a disk, a circle, in the first place, right? And there's other exotic things, such as black hole jets. Eventually what happens is, if you have certain configurations of black holes, you can get these really cool jets that are launched from the middle of the black hole in both directions, and that sort of acts to heat the galaxy up on its own, which is pretty cool. And so this has also been modeled. Now, the problem is, how do you put all of this in, right? In the words of Douglas Adams, the famous Hitchhiker's Guide to the Galaxy author, don't panic. We have something to our rescue, and that's called subgrid models. And what does this mean? So imagine you want to simulate an entire galaxy, right? But you want to also have all these small, tiny pieces of physics in it. Now, as I mentioned, one of the pieces of physics is, for example, a supernova explosion, which is so tiny that you can never actually hope to resolve this in any given simulation ever. So for comparison, it's as though you were waving around a grain of rice and the entire rotation of the Earth would be affected. So this is sort of the range of scales that we are talking about. So that makes it hard to do this in any sort of physics that you want to do. And these simulations are also incredibly challenging to do because they're sort of all in 3 dimensions, right? Because you have X, Y, Z, and you're also evolving it in time. So effectively it becomes a 4-dimensional problem. So you can imagine that doing any sort of thing like this, you would need loads and loads of computational power. And this has only been possible in about the past 2 decades or so because of advances in computer science. So this is how advances in other fields, especially in computer science, impact astronomy in general. Because that has led to increasing understanding of a lot of fields in astronomy. Now, how do subgrid models work? So this is an example of the range of scales that you are dealing with. So black holes are sort of the smallest scale, and they also move around and change on really short time scales, which means they're pretty rapid. And on the largest scale, you have sort of multiple galaxies binding together, which happens the slowest. So to connect all of this physics, what you do is you put something called a subgrid model into your code. And what that means is that you sort of have a mathematical prescription by saying that, okay, this is the impact one supernova explosion would have on the entire galaxy. So what that in practice would look like, you could say, okay, I've injected this much energy into this particle, and that's all. So you don't actually have to fully do and fully resolve a supernova explosion in your code, which would be impossible, but you sort of mimic the effects it would have on the code. And so you can have subgrid models for all these small things that you really don't want to care about as much, or you can't care about as much. So that's what a lot of the big codes do, which is you include all of these little tiny pieces of physics, and then you put subgrid models for the ones that you can't resolve. And then for the rest of it, you just make them evolve with time. So in summary, what you have is you have some pieces of physics which are just modules, so to say, and then you have your basic equations that you're trying to evolve. What does that look like in practice? Here I'm showing you one such simulation. This starts with really old galaxy conditions, or really old universe conditions actually, and eventually you see a black hole forms at the center, which is where you have all the mass concentrated. So this is showing you a map of density. And you can see a lot of the cold gas is sort of coming in, and the black hole is sort of accreting it towards itself. You can see these long structures, these are called filaments, which sort of connect other galaxies to other different galaxies. And at the nodes of these filaments are black holes and small galaxies which will eventually form. Here you can see the star formation. So all the white particles here are stars that are being formed because the gas is dense enough to form stars in those locations. So this is sort of showing you a 3D rotated view of the whole thing. The galaxy is not formed yet, but it's very close to being formed because you can see some evidence of circularization, which means you can see some effect of angular momentum. In the green is something called gas metallicity, which is basically only showing you everything that's above hydrogen. So astronomers famously like to call everything about hydrogen a metal for some reason. It's because we don't really care about those other things. Well, to some extent. But here's what it would look like if you were to see it using a telescope at this point. This is quite old, so you wouldn't actually see something like this at the moment. But as you see now, as it evolves, you start to see the formation of a disk. You can start to see remnants of a disk. You can also even start to see spirals forming, spiral arms, yes.
So all that motion, is that due to gravitational effects?
Mostly due to gravitational effects.
No magnetic field this time?
This, I think, I'm actually not sure if this has magnetic fields or not. There are simulations that include magnetic fields in them. This might have magnetic fields in it also. I'm not fully sure. I can double check for you. Right, so that's the idea. And now you can see you have a disk, right? And you have a galaxy. So you can see how the gas is now collated, and you can now see this spiral structure. So this was famously made by the illustrious T&GT, which they were not one of the first people to do galaxy formation, but now one of the front runners of galaxy formation simulations, because they sort of have the best simulations there. And the reason I say they're the best, because once you have these simulations, you can sort of check whether, I guess it's starting again, but that's fine. Once you have these simulations, you can check whether it matches observations well or not. And in their case, it matches pretty well, so we know that they're doing something right. The one problem with such simulations, though, is that you don't fully know which piece of physics is doing what. Because you've included every single piece of physics in it, it's sort of hard to disentangle what exactly is causing what thing. So if you want to go back to the original question, which said that, okay, where is the extra cold gas coming from? Sure, you can say that it comes from maybe this accretion stream itself, but what exactly is it? Is it just gravity? Does it matter whether angular momentum is doing anything to it? Does it matter whether you have magnetic fields? Which piece of physics is important in doing this? So there's lots of other people that have this other approach to doing such simulations. The other approach is that you, instead of simulating the entire galaxy, where you also don't have supernovae resolved, you can sort of zoom into a small patch of the galaxy and just try to simulate that. So the idea here is that you take a small slice of the disk of the Milky Way and you look at it edge on, and then you have this small patch of gas in the middle, which is supposed to be the Milky Way disk, and then you let supernova explode and see what happens. So this way you can actually resolve the supernovae, and you can actually infer some of the important physics that's happening. Instead of looking at this global picture, you zoom into the local picture and see what's happening. So this is sort of the other way to do it. And what do such simulations tell us? So here is one example of these simulations. This is sort of, well, it's not the initial condition, but is like the initial condition. So you can see the gas disk in the middle. That's sort of the disk of the Milky Way, and you're looking at it edge on. And in this code, what the authors have done is they put in supernova explosions, and you can see maps of temperature, velocity, density, pressure, and the magnetic field. So this is sort of the physics that they put in. So this video was actually made by Brent Tan, who was a former grad student in our group, but is now a postdoc at Cornell. So he did this work as a grad student, which is pretty cool. But what you see in these simulations then is, I'm going to let it run, and you'll see soon enough that you'll have supernova exploding in the center, and you'll see how it drives these really cool winds and really cool outflows because of that explosion. So it's forming, there it is. You have the first supernova explosion, and it's driven this huge wind outside the box. And these are famously called galactic winds or galactic outflows. So when you have a bunch of supernovae that explode together, they're called supernovas, which is a cool term, right? And then eventually what happens is the gas starts, well, the supernova is sort of depleted, and then the gas sort of falls down. I don't know if the video is, yeah, there it is. So it's sort of like quenched in a sense. And that's because you've sort of released all of the gas away, and you sort of expended all the energy you had, and now there's nowhere to go except gravity, because you have the disk there. So it just falls back down. But eventually this will proceed in cycles, because once you have enough gas in the center, you'll form new stars, and you'll have new supernova explosions. So this proceeds in cycles, or these oscillations that keep on happening. So this is sort of the self-regulating mechanism of the disk of the galaxy, in which it sort of sustains itself. So it's this tight interplay between star formation, supernova explosions, and how much gravity there is. So it sort of always tries to balance itself out, in a sense. Well, you could not have known about this if you looked at the global simulation. This is only evident if you actually did have supernovae that were resolved. So that's the idea here. Now, the approach that our group takes is even more extreme, which is you sort of zoom in to those cold clouds that you see. So what our original question was, we have some extra fuel, which we hadn't accounted for, and we want to see what happens to that extra fuel, and whether the galaxy is able to obtain that extra fuel and use it efficiently for star formation. And what is all this extra fuel? All this extra fuel is nothing but cold gas, which is coming from these winds themselves. So in the left panel, everything that's yellow is hot. It's really, really hot. All of that is eventually going to get escaped. But the cold stuff are those blue circles, are the tiny blue objects that we see, which we call cold clouds. This you can actually observe. So when I showed you the pictures of galaxies edge on, those cold clouds were what you were seeing. So what we do is we zoom into one single cold cloud and see what happens to its evolution, right? So what we can do is we can assume that this cloud is a single sphere, and then we blow a wind. That's the whole idea. It's literally taking it at the smallest scale and seeing what happens when you have a cold cloud and you blow a hot wind on it. What happens to its evolution? So this is a simulation that's showing that to you. So in the background you have a hot medium, which is sort of the hot CGM of the circumgalactic medium, so to say. And then you have an overdense cloud, which has about 100 times as dense as the background, and it's 100 times colder than the background as well. And you have the wind that's blowing from the left or the right. So if you just have this setup, and you see what happens, as the cloud evolves, it deforms a little bit. It starts to mix with the background, and as it mixes, it sort of blends away with the background as well, and eventually the cloud just dies. Right? But that's bad news for us. That means we've lost the fuel that we needed for star formation. Now, this is where it becomes important to consider the second piece of physics, which is radiative cooling. So we didn't take that into account yet. But what happens if you do take cooling into account? Here, the magic is that once you have the cloud, it does mix with the background, but it also cools. And you can get more cold gas as a result of that. So if you include radiative cooling, you sort of get more cold stuff than what you started with, which is really good for us, because that means we've ended up with more fuel than what we started with. So this is sort of the simulation that shows you how this works. When you include radiative cooling, you end up with more cold gas, which, again, is good news for us. So the other side of the story is what happens when they fall down. And so why do we care about this? Well, of course, you've launched a lot of cold gas out, but are you able to bring it back down to the disk as well, so that it can really serve as fuel for star formation? So this is sort of the reverse process. Instead of now looking at a wind that's blowing on a cloud, you take a cloud and you make it fall under gravity and see what that does. And again, the conditions are sort of the exact same thing. So here you have two blobs. One of them is showing you density, one is showing you temperature of the same thing. And you just let them fall under gravity and see how that works. And as you would expect, it's sort of a similar story, but it seems like the cloud is first getting destroyed. It's getting mixed into the background, but then cooling becomes fast enough and is able to preserve it. So that's just replaying the simulation. But eventually, you also end up, if you have cooling, with a lot of gas. More gas than what you started with. So that's good. That means that when you went up, you also got more gas, and when you're going down with radiative cooling, you still have a lot of gas with you. So is that the end of the story? Not quite. It's because we did not consider what magnetic fields did, which is my favorite part of this talk. Now, what is the impact of magnetic fields? What magnetic fields do is they basically act as taut ropes. So when I said you could actually consider the plasma as just a fluid, I lied to you a little bit. You have to consider them as fluids with magnetic fields. And once you do that, then you can actually reconstruct everything that happens. So the way this works is that imagine you're playing a game of tug of war, and imagine you try to deform the rope a little bit, right? The rope would actually want to move back to its original position. So it'll exert a force so that it tries to be as straight as possible. So that a similar thing happens with plasma as well. If you try to do this in a plasma, the plasma will want to stick to the magnetic field lines, and they'll want to stick to the way in which they were moving. Sort of like Newton's first law of motion, very similar to that. An object in motion wants to stay in the state that it wasn't. So but it actually matters which direction you have magnetic fields in, which is interesting, because now it adds an extra layer of complexity. So what I can tell you now is that if you have aligned magnetic fields, which is the case on the right side, so if your cloud is falling straight vertically down, and you have magnetic fields that are also vertical, then you actually get less mixing. Now, why would that be the case? It's just because if you look at the interface between the cold cloud and the hot background, you initially, what you used to have is mixing, and when you get mixing, you can have more cooling as well. But now that you stop mixing, you also stop cooling. Well, why would you stop mixing? That's just because everything wants to be straight. You don't want any twists and turns to happen. So that's sort of is bad for you. But what do you think happens when you have horizontal things?
We're mixing.
Yes. But why do you get more mixing? But the idea behind that is the following. If you start with horizontal magnetic fields and you start to make the cloud fall, it will deform the magnetic fields. And as it's deforming it, the cloud also gets squished. Right? So the cloud gets squished in this direction because it's being sandwiched between these magnetic fields. Right? At the same time, because you are sort of moving against what this tension force would be, you're also forcing it to stay where it was. Right? And when you force it to stay where it was, you allow cooling more time to have more time. And when you have more time to cool, you have more cold gas. That's why it helps, which is pretty cool. So it depends on which way your magnetic field is aligned, and based on that, you can get more cold gas or less. So you can see this in simulations as well. So here, as you can see, the cloud is getting squished because of those magnetic field lines, right? On the right side, you can see the strength of the magnetic field. And it gets squished so much that you basically just end up with one thin line, and that's about it. But the interesting thing about this is, you can look at this from the other side. And what I mean by the other side is that if you squish something in one direction, it needs to go somewhere, right? So it'll expand in the other direction. That's the whole idea. So if you take your box, you rotate it by 90 degrees, you'll see something interesting. As it gets squished in that direction, it splits apart in the other direction. And it forms these really cool filamentary structures, right? And the reason this is important is because oftentimes in galaxies, you see a lot of filaments. In observations, you'll see a lot of filaments. And so perhaps this is one way in which filaments are formed in the first place. So that's pretty cool. But what this means is that the direction in which your magnetic field is aligned is able to influence the star formation rate, which is nice. In practice, of course, this is a very idealized setup, and that's the one downside of doing something like this, which is that if you look at any observations in real life, you don't ever have something that's completely straight or that's completely horizontal. You'll always have some combination of those two. So that makes the story a little bit more complicated. So in effect, you'll have a combination of those two things, of the case when you have vertical magnetic fields and the case when you have horizontal magnetic fields. So that's what happens to a cold cloud. And so you can, of course, test this with observations. You can see that it works. Now, this is sort of a biased way of looking at it because we are only favoring one sort of model for how stars form in the galaxy. There's a couple other models that are in practice. One of them is, for example, through something called Ram pressure stripping, which what that means is you must have seen in the planetarium, you saw videos of the large and the small Magellanic clouds. So what those clouds do is that, well, you can think of them as tiny galaxies that are there within the CGM of our galaxy. And sometimes what happens is they're running through the galaxy so fast that they actually strip some material away. And that stripped material can actually fall down and then form stars as well. That's the other model that I didn't talk about. There's yet another model, which is known as the precipitation type model, which means that if you just start with a hot medium, you can actually have cold stuff condense out of it on its own. A very interesting result. And a lot of people argue that it is some combination of this, of cold cloud infall through supernova explosions and through this gas stripping mechanism.
Ish, can I ask you a question?
Yes.
When you say cold gas, is it, you're saying that a gas is cold, or is that you're transferring from a plasma, a hydrogen, you're going to a neutral hydrogen?
Sort of. So what I mean is so the background of the CGM, which is the circumgalactic medium, is at about 1,000,000 Kelvin. And the cold clouds themselves are at about 10,000 Kelvin.
So it's still a plasma.
It's still a plasma.
Okay.
Yeah, exactly. And it's all atomic, so to say.
Okay.
Yeah. So that's what I said about this. But, well, this means good news for us. This means the galaxies can live longer than what we had thought, and they won't just die within 2 billion years. We have a few extra billion years to live. So, now the idea is that, well, since I talked about all this, can you actually test this? And one of the reasons I asked this question is because, well, theorists like to theorize about a lot of things, and a lot of things in astronomy are not testable because everything is so far away that we aren't able to actually get good quality observations to really test them. In this case, however, it's uniquely a very good exception because we actually see something very similar happen, not in our galaxy, but something much closer than that, and that is our sun. And now you might be wondering, well, how is galaxy formation related to stars, and how is that related to suns in the first place? And the answer to that question is in this video. So this video was taken by NASA in 2012 by something known as the Solar Dynamics Observatory, or the SBAU. That's sort of like a satellite in space, which is only designed to look at the sun at all times. So they look at different frequencies, they look at different wavelength bands. One of the devices aboard that satellite is there to look at the atmosphere of the sun, also known as the solar corona. A lot of people might have known about this. It's very visible during solar eclipses. You can see a very bright outline along the sun, or along the moon, in the case of the eclipse, and that's actually showing you the atmosphere of the sun, which is pretty hot and pretty bright. Otherwise, normally you would not see it because the sun itself is way brighter. But once it's sort of shadowed by the moon, then you can see the whole layer around it, which is the solar corona. Now, as you'll see in this video, something very interesting happens. So there's a huge flare that's called a flaring event, and what that does is it expels these really large loops called coronal loops, and these loops basically are magnetic field lines. And the stuff that's falling down is rain on the sun, which is basically just clumps of plasma that are falling down, right? And in this case, the magnetic field is so strong that all of this plasma is sort of tightly confined along these field lines and has nowhere else to go. So it falls along these field lines because there's nothing else to do. This is something similar to what happens in prominences. In this case, there's a small difference, but this is called coronal rain, and it's been observed in the sun for the past multiple decades. There's a few explanations for this, but once you realize that they're the same thing as what happens in the galaxy, you'll be amazed. Now, why is it that this is the same thing as what happens in the galaxy? So this is sort of a cartoon picture of what I'm trying to talk about. So the surface of the sun is in orange. The photosphere is what you actually observe. That's where the last photon escapes the sun and it hits your eyes. So that's sort of the surface. And then on this surface, you have these loops, which are called coronal loops, and these are basically just reflections of the magnetic field itself. Now, the solar corona is at 1,000,000 Kelvin, which rings some bells. It's because so is the circumgalactic medium of our galaxy. And it turns out that the clouds that fall through these loops, those are the blue circles, are at about 10,000 Kelvin, which is again exactly the same thing as what happens in the galaxy. So we can actually stare at the sun, for which we have days and days, years and years of data, and try to verify if our model works or not. The only difference, however, is that here the magnetic field is extremely strong. In this case, the importance of the magnetic field is about 3 orders of magnitude more, which means in relative terms, it's about 1,000 times more important to have magnetic fields here, which is why they play a much more important role. But plasma physics, magnetic fields, radiative cooling, all of this is the same physics that happens in the galaxy. the same physics that happens in the surface of the sun. So we can test it out. Now, there's multiple ways in the way in which this can happen. One of them is that you can sort of precipitate them, as I told you about, which is that you can start with just a uniform box of plasma, and then you'll form cold clouds out of it. And then those clouds just fall along. The other way to do it, as you saw in the video, is through flares, which means there's stuff that's been sent out from the surface of the sun into these loops, and then it falls back down. Something similar to the galaxy. So, in order to graduate, I need to show that this works. That my theories actually work. So, that'll be part of my thesis. But yeah, I tried to keep this short so that you can ask me loads of questions if you want. That's more fun anyways. But yes, thanks so much.
Good. You take Q&A for a while?
Of course, yeah.
All right. Who's going to be first?
You said something about how galaxies sustain themselves.
Yes.
But as stars form, they start fusion reactions and consume hydrogen.
Yes.
So, and they turn into supernovae.
Yes.
Is there an estimate when they'll run out of hydrogen? Or
Well, yeah. So, I mean, all stars have sort of a life cycle. And based on certain characteristics, you can pinpoint in what part of the life cycle the star is on. And based on that, you can also estimate, at what point will it die. So you can do that for individual stars. In principle, I guess, yes, you could do it for all of the stars and say, how long will it take for all the stars to die? But, I mean, I guess that's an academic exercise because eventually you'll have new stars forming as well. And also at this moment, you can't see that many stars forming because you only get one snapshot. Right. So you can do it for the stars that you observe, but I mean, there's quite a lot of stars in the Milky Way. Yeah.
Ish, go ahead and open up your laptop so we can see you on,
Yes.
on Zoom.
Mr. President,
Yes.
Thank you.
have you published this work yet?
Not the solar. Well, the solar stuff partially.
Okay.
The galaxy stuff I did. Yes.
Did you send
That's
it?
lovely.
Yes, I can send it to you.
Very excellent. Now, when when the solar flare lifts up from it looks like a magnetic field line lifts out of the sun.
Yes.
And it takes a lot of plasma with it.
Yes.
They're sort of bound together.
Yes.
And then you see all this plasma or the material flowing back down. Where is it getting at? Is that magnetic field line cooling the atmosphere of the sun so that you get new material that's kind of colder and now it falls back down to the sun?
Right. So that's a good question. So there's actually two types of coronal rain that happen. There's one type which I showed you here. It's called flare-driven rain, which means that the rain itself was caused after a flaring event happened. So in this case, what happens is when the plasma itself is lifted off, when the field lines get lifted off from the surface of the sun, they contain plasma in themselves as well. And then eventually they reach at apex because whatever mechanism sort of launched them in the first place sort of died out. And then eventually they fall back down. But there's another type of rain that's called quiescent coronal rain, which does not need this process to happen. So occasionally what you'll see is, you'll just see a coronal loop, and then plasma just randomly appears. So in that case, what people have been trying to think about is, so the surface of the sun itself is very turbulent, so to speak. And so there's lots of heating that's going on the surface of the sun. So if you can have sort of randomized heating on the foot points, which means at the place where the loops connect to the surface of the sun, you can sort of eject some bit of plasma into these coronal loops, which can go up. It's still hot, it's all still hot, but once they reach the top, they can cool, and then they can fall back down, in which case you can see them just out of thin air. Another way to do it, which is what I suppose we are pushing for, is the idea that when you have quiescent rain, coronal rain, you don't need something to be pushed out. As long as there's plasma, you can just get it. You don't need something to go up. But again, quiescent rain is more rare, but it does happen. Flare-driven rain is more commonly observed, in which case you have actually lifted up plasma. from the surface of the sun to go up.
Back here?
Okay.
Sorry.
Lady first?
When you started your research, did you expect that you'd use coronal rain to test your theories, or did you think you were going to use something else?
Definitely not. I actually didn't think I would be able to test it at all, as with most things in astrophysics. But that was the cool, I mean, I didn't know coronal rain existed, but then I saw these videos. Well, I guess, yeah, my advisor and I saw these videos and they're like, oh, there's a very clear application to this. So then we thought that, okay, maybe we can do something in this field. So historically, it's been the case that after about the 1970s, the solar physics community and the astrophysics community have sort of like grown apart. The last person to unify them was, what's his name? Was John Bocal, who solved the solar neutrino problem. And he was the last astrophysicist that worked on solar physics. Since then, you have a whole bunch of heliophysicists and a whole bunch of astrophysicists that don't talk to each other. So maybe this is one way to unite our fields. Yeah.
Let's tell them first, and thank you.
You talked about the importance of the direction of the magnetic field. Is there some way to tell which direction the magnetic field is?
Yes. So here's what we get in the crux of observations that this is the bane of the existence of observers. Observers hate magnetic fields. And that's precisely the reason, because it's really hard to observe magnetic fields, and it's really hard to understand, one, how strong they are, and two, what direction they are in. So it's particularly hard to do this in our galaxy, because in other galaxies you can see them in their glory, but we are sort of biased observers because we're sitting inside the galaxy. So it's hard to look at our own stuff. But observers have some idea about what's the magnetic field strength and what the magnetic field geometry is in the disk. And they have some, to a lesser degree, idea about what the magnetic fields look like in the CGM. And in particular, what makes the CGM even more difficult is that it's not as dense as the disk, so you can easily just miss it when you're looking at things. And our background sources will easily just overtake what the CGM is. So it's really hard to constrain that, which is why the best estimates for what the magnetic field strength is in the CGM is just an upper limit. It's not, there's no lower limit to it. That's all that we have. But in the disk itself, we actually have a decently good idea about what the field strength is. So that's a recurring problem. Observers are developing methods to try to fix this and try to make better estimates. But I guess that's ongoing work.
And the direction can be assumed by the motion? Is that the idea?
Yeah, I mean, yes. So I think what observers use to find the direction is something called polarization, which is that you can see emission coming from particles, right? But based on how polarized they are. So if you think about an electromagnetic wave, every electromagnetic wave has some degree of polarization. So based on how polarized it is, you can sort of infer which way the field line is, things like that. But that's in process. There's also, you can use the rotation as well, but I think the rotation measurement is more for the strength and not the direction itself. Yeah.
Okay, sir.
Yeah, so you're kind of working by analogy to these solar things, but isn't there like a really big mystery about these solar things where the corona is just way hotter than the...
Yes,
so,
yes.
We have no idea how that is.
Right. So this is part of the reason why this question is important for solar physicists and not just like a test bed for the astronomy people. Because in solar physics, the main question they are trying to answer is what causes the solar corona to be this hot. Because it is, I mean, the surface of the sun is 5,000 degrees Kelvin, but the corona is 1,000,000 degrees Kelvin. So what is making it so hot? And it's the atmosphere. It should be colder, if anything. So no one knows the answer to that question, but a lot of people think that the cooling process is sort of, so just cooling and heating are sort of two sides of the same coin. And what we're trying to analyze is the cooling process, or how the precipitation works. So maybe, in a sense, if we try to find out more about how the cooling process works, that will help us understand what the heating process is. So coronal rain, that's why it has in the literature been used as sort of a test marker for how heating happens, actually. Which is why this question is interesting for the solar people.
Well, maybe turn it the other way around. Maybe your galactic observations can explain the sun.
Probably. Although I think in the galaxy we have a pretty good idea for why the CGM is that hot, but we have no idea why the sun is the solar atmosphere is that hot. So it doesn't fully work that way, unfortunately. Yeah.
Okay, far back first, then you.
I think the Parker probe just found a whole bunch of little micro flares going on in the spicule type structure, and they think that might contribute a lot to the heating.
Yes, it would. So that's the model that I was talking about, which is that these spicules have randomized heating, and that sort of launches things into these loops, and that can then precipitate down. So that is actually a very important model that people do look at. And yeah, so again, most people think that it's going to be some combination. I mean, mostly it is that, which is what you're talking about. Some combination of that, some combination of just pure precipitation, and well, there's a couple other models as well, but. Yeah, the Parker probe is actually very important, and I haven't looked at their observations much, but I should start looking at those because they're actually pretty good.
Got 8:25, we got plenty of time. Dr. Sean.
I was just wondering, we had a great speaker last year was talking about all the dwarf galaxies around the Milky Way that are satellites. Do you know, like, how does the Magellanic streams compare to the amount of matter that we get from those galaxies compared to?
Yes, so yeah, that's a good question. I don't know if anyone has done a full calculation showing which thing is more important. Partly because I don't know if there's any observation, well, you can't have observations that show how much cold stuff is actually falling down, because you just see it there and that's all. Yeah, I mean, there's people in the community who actually push for the satellite land pressure stripping model as opposed to the precipitation models that I talked about, but they're always fighting about it, saying which one is more important. So I think it's still an unresolved question because each of those fields is active and no one has sort of admitted defeat to the other. So that's still like a little unresolved thing at the moment, I would say. Yeah.
Okay, in the middle.
You talked about originally you thought it was 2 to 3 billion years we run out of gas. If you extended that out further, I wonder if taking into account our eventual merger within 31, how that would impact that.
Right, so this does not assume that. If you do merge, that's going to bring up a host of other things.
It's
So.
going to have a massive star formation.
Yes, exactly, yes. So that's actually going to help our chances. Well, it might destroy us, but it'll make the Milky Way a bit longer.
Yeah, no comment.
Bruce, do you have a question? You usually. Something must have occurred to you, Bruce Murdoch, president of the Santa Barbara Theater Organ Society. It's in our club.
I was just wondering, what are the magnitude of the magnetic fields you're talking about?
Yes, so in the disk of the galaxy, it's supposed to be about 5 microgauss. So a Gauss is about, so if you do a CT scan, for example.
Gauss is 1/10,000th of a Tesla.
1/10,000 Tesla, yeah. CT scans would be about 3 Tesla. And so this is about 5 microgauss. So micro is 10 to the minus 6. That's tiny, yes. And in the CGM, which is the stuff outside, that's going to be about an order of magnitude lower than that. So it's even smaller.
In the very back.
What is the source of the magnetic fields for the galaxy? The individual stars have their magnetic fields, but what's the dominant source of the magnetic field for the entire galaxy?
So this question can become very deep very quickly because there's actually a conference in the KITT going on right now, in which they discuss that very question. So so the thing is, a lot of pure plasma theorists would believe that there was some seed magnetic field in the beginning of the universe, and that seed magnetic field sort of got enhanced by certain plasma instabilities. And because that got enhanced, and because the way I said plasma physics works, the plasma sort of attaches itself to the magnetic field lines, and so any twists and any turns that you get will also twist and turn the magnetic fields. And so you can imagine a situation where if you have a loop of magnetic field and you sort of twist it and loop it over itself, you've doubled the magnetic field strength. And now you can imagine there's turbulence going on everywhere. So that turbulence can eventually do things like this. And this is called the dynamo effect, which is how magnetic fields get enhanced on their own just because of turbulence. That's one way to answer it. There's also the whole plasma physics side of things, which is there's certain instabilities that can operate independent of this dynamo action. The other thing that is actually perhaps the most important in the galaxy itself is the rotation itself. So, say you had a loop of magnetic fields that you started with, and the galaxy is the loop, and then you go through one rotation, you've sort of wound that wire along itself, right? And then you go through multiple rotations and you wound that wire multiple times. So you sort of wound the magnetic field around itself, which means you've enhanced its strength. Which is why in the galaxy disk itself, you actually see that primarily the field is toroidal, which means it's like this circle around the disk. So that's where most of the field in the disk comes from. Now, in the CGM, what happens is, yes, you can get these things like outflows, these supernova explosions, or even the black hole itself has these jets, things like that. In some cases, those expel magnetic fields out, and that leads to these wandering magnetic field lines just out in the galaxy. That can also happen. But again, we have a harder time constraining that than the other things. But yeah.
In the back.
Hi. Yeah, so you have these simulations that show the ejection and then the coda and then the precipitation. Can we observe different galaxies where this process might be going on at different stages to help inform the theory?
So I think there's effort to do this more recently. So one of the first pictures that I showed was of these clouds getting ejected. For some reason, well, yes, okay, so I should say, there's a lot of cloud observations that show them in a wing, which is that you have sort of an outburst and then the clouds are sort of in that outburst. There's also a lot of observations calling things like HVCs, which are high velocity clouds. Most people now, actually, because of our group, not me, but people in our group, we now think that most high velocity clouds, so high velocity clouds have been explored in the literature for the past at least 2 decades, if not 3. And their origin has been unclear. But the only, perhaps, well, I should say the only, but I'm biased. The only way to get high velocity clouds is when they're falling down. That's the only way you can get velocities that are high enough that they're called high velocity clouds. So that's one. The other thing the other things that are observed is called IDCs, which are intermediate velocity clouds, which people think could also be some combination of either going out or going in. I think in actual observations, there was someone from Johns Hopkins who's working on it, and he has this whole map of all the clouds in the Milky Way at the moment, and the kinematics, so he can trace all the velocities and where it's going and things like that. And I think he did conclude that most of the high velocity clouds in our galaxy are actually falling down instead of going up. So that's sort of like good confirmation that this works. And then there's a host of observations showing clouds that are going out. Actually, that was the first thing that motivated the study. There's fewer observations showing clouds that go into the disk. So, yeah.
Any other hands?
Dark matter. If our galaxy is 80% dark matter, how does that affect the gravitational effects of things?
Yes. So I guess I did not talk about dark matter much, but that's because in terms of the plasma physics, it doesn't have much effect. Because it's dark, which means that it doesn't interact with anything except gravitationally, which is what you said. So the only way in which dark matter does have a role is in terms of the gravitational potential. So when you do the simulations that I showed you, which not the individual cloud ones, but actually even the individual cloud ones, if the ones that are falling, if you sort of have to assume some sort of gravitational profile, right? Because they don't just fall under constant gravity. The closer you get to the disk, the stronger the gravity becomes. And so these sort of gravitational profiles that you have to assume all come from dark matter models, because the primary thing that's sort of pulling it down is dark matter. Well, to some extent it's the galaxy, but a lot of it is also dark matter, because dark matter sort of dominates the gravitational profile of a lot of the galaxies. So that's where we assume it. Of course, when you are doing the bigger simulations, you have to sort of, in some cases, they self-consistently evolve dark matter, which is much harder to do, which is you create dark matter on its own. And then the field will sort of know itself. Like it will know what the field is because you have that much dark matter in there. That's harder to do. So some people just assume that there's some gravitational profile that you would get if you have this much stuff, and then you just go with it. So that's the way in which dark matter will affect things.
Thank you.
Got about 10 minutes. Can you take one dumb question?
Yes.
Ish, I may be on the board of Santa Barbara's astronomy club, but I represent the armchair astronomers division versus the ex-engineers and retired physicists. So I got a lot of what you said tonight, but I'm lost on a lot of the rest of it. Here's a simple one. Matter I grew up with, learned was solid, liquid, or gas. And only less than half my life ago did I learn about this dreaded
Plasma.
plasma. Yeah, everything's burning.
Yeah.
I heard about the word vaporize when you talk about atomic bombs, and oh my God, well, that's as good way to go as any. And then I become plasma. Right? Matter can exist as solid or liquid, probably only on planets. Is the rest of it just gases or fast gases that are plasma?
Probably. Maybe the cores of stars, it's pretty dense. So in the middle of stars, you can have so much gravity that you can get solids. In some cases, you can have, so once you have a supernova explosion, once all the gas is removed, once the explosion is done, in some cases what happens is your star sort of contracts and becomes a neutron star. And the reason we call it a neutron star is that the gravity is so strong that the inside of a neutron star contains exotic phenomena. And what I mean by exotic phenomena is that stuff there is none of the states that we know. Because there's so much pressure that all the neutrons are sort of collected into this one tiny pocket. They're squeezed so much that we have no idea what we call that state of matter. And that's why they're called neutron stars, because you can have all these weird things happen inside stars. So it's neither a solid nor a liquid. You can imagine it's a solid, but it's even more compact than that.
But the particles are moving like great Godzilla.
Yeah, but now they have no space to move at all. That's what happens in a neutron star. They're sort of fixed because there's no space to move around. So there you can have things like neutron degeneracy matter, which is like, we have no idea what that is. There's people working on this, and I mean, everything is just a theoretical model, because again, we can't just dig a hole inside a neutron star and see what's there. So everything is all theory, and all you can see is what happens in the crust of a neutron star. So this whole field of astroseismology, which is you can measure how the crust moves, and based on that, you can infer what the profile of density looks like inside, which is pretty cool. But again, it's all theory. We have no idea.
Do you suppose after the Big Bang, the
Yes.
first galaxies that formed were nothing but hydrogen stars with hydrogen planets? Is it possible to know
Hydrogen
that?
planets.
I mean, they didn't have the new stuff, did they? That takes several generations of exploding
Perhaps,
stars
yeah.
later.
Yeah, I think in the beginning you had these theorized population 3 stars, right? That's what you call them, which is like the progenitors of the stars, which I would guess are composed a lot, mostly hydrogen, some helium, things like that. But then eventually when you form stars, I don't know at what, I mean, I'm not a stars person, as you saw, but eventually what happens is I think at some point in the evolution, you start having fusion, right? And so you can have heavier metals form in the core of the stars. I'm not sure at what point after the Big Bang that happened, but initially, yes. I mean, it will be dominated by hydrogen, for sure.
One last question, anybody? Yes?
Yeah, it's another kind of ignorant question, sorry.
That's fine.
But is there any way to simulate on Earth with physical items this process? Are there any things that are analogous to?
So, that's a good question. So, it depends on how detailed you want it to be. Right? So, I mean, so if you just want to do fluids, that's easy. Right? If you want to do fluids and magnetic fields, that's really hard. No one can do that. But if you want to do, say, if you want to simulate very basic plasma effects, you can create plasma on Earth, right? So, in principle, if you do create plasma, I mean, you see neon lights, right? That's all just plasma. It's just low temperature plasma. But eventually what you could, I mean, there's lots of experiments that are trying to do this, which is they're trying to probe certain plasma physics phenomenon on Earth with lab experiments, with some success, not a lot of success, because again, the scales in the galaxy are just so huge that you can't ever replicate that. But you can still hope to probe certain small instabilities and certain small processes that are happening. So there are efforts to do this. There are efforts to have lab experiments, but I think all the lab experiments are always going to be limited in terms of the range of scales that they can probe. It's always going to be just small ones. But there are efforts that do this. So that is an ongoing area of research. Yeah.
You did good, and let's get you. Filipenko in the big stadium above our Fleischman Auditorium. And please tune in on Monday mornings, 11 o'clock for our Astro Hour.
Yeah.
My friend Ish Kaul, I have for you our official, these are being sold and they're going to be rare. This is our cup, that's your check, your token, and your astronomy.
Just a reminder that it's 8:41 or 42 since I looked, and we need to be out of the parking lot by what, 9 o'clock? Is that what we're told? Yeah.
Socialize with your new friends as you head back to the car. All right?
Buy a whole building. That's lots of cool
Thanks so much. Thank you. Thank you.
I'll dress up. I'll wear the tie.
But within that, some certain structure. So that's what it feels that you're expecting. But that's yeah, it's very there's we have all the increments because we think in and so we can call that science in production. So it's sort of so that's how we but probably. Yeah.
That was fun. He was a very good speaker.
Yeah, pretty good. Just a few words I couldn't quite catch.
Those I think really got it.